Hi, this is a project about detecting tumor cells from whole slice images with the help of deep learning. The original slide has a size of 100,000 width with 100,000 length, but the tumor is about 1,000 length with 100 width, which makes it harder to distinguish whether a cell is a tumor or not. About the code, this part is to install OpenSlide tools, which will help us to analyze each slide later. And this part is to import what kinds of Python libraries we will use later, such as NumPy, Pandas, TensorFlow, Skimage, OpenSlide, and so on. And rest is to download the tumor slice and the mask of a tumor. Then I read the slides and mask with the OpenSlide function, and this is a sampler of the whole slide and mask. Since one pixel in level 7 matches with one patch in level 1, and the patch has a size of 128 of length and 128 of width. This one is the patch with tumor cells, and this one is patch with normal cells. Then I define a function getPatches to get main information of each pixel. First, I filter those non-cell pixels and based on their grid value, and then judge the pixels are tumors or not, and record their location with row and column numbers. As you can see, this is what we can get from this function. This one filled the non-cell pixels, and this one didn't fill them. Since the data is unbalanced, that being said, the negative samples are nearly 20 times of the number of positive samples. So here comes the downstamp function, which is used to randomly choose certain number of negative samples rather than using them all. And since the data is too large for us to fit into memory all in one time, I define a data generator to generate batches of training samples and test samples. By the way, in the training part, the function will generate 4 other positive samples for each positive sample by using flipping the patches, which is data augmentation. Here is the model I construct. Since the input and output are all pictures, so I adopt fully convolutional network, which have a convert 2D transpose layer in the last of the model. Then I feed data into the model and train the model. This is a predict function, and this one is used to draw a heat map of each patch, which show the probability of a patch being a tumor cell. And here is an example. This one is the original patch. This one is the mask of that patch. And this is the heat map of that patch, where the red means high probability and the blue means no probability. This is a predictor mask. Then there are metrics to judge the performance of my model. There are confusion metric and AUC value, that's area under curve. And this is ROC curve, and the AUC value is 0.97. Using confusion metric, we can calculate the accuracy, recall, precision, and F1 score. Finally, this part is to predict heat map of each patch, and then combine all the predict heat map with the original slide to show the probability of each part being tumor cells. And as you can see, this is a final result, the heat map we produced. Besides what I've done above, I also try other types of models to see which one is better. I have the same procedure above, into model with VGG16 cover base and exception cover base using the transfer learning method, which are pre-trained on ImageNet. I also tried model without downsample. The result is shown here. As we can see, the performance of our original model works better. And finally, as for AOC value, the model has exactly same results, whether it has a downsample or not, which means the AOC value is a stable metric when it comes to unbalanced data.